Swayam Prabha. Digital India. Educated India.
Okay, good morning. So in the last few classes, we were talking about cellulose. Cellulose can be extracted from various biomass, mostly from agriculture waste. And these isolation process typically involve sequence of steps in order to remove hemicellulose, lignin, and silica and other impurities. This could be a combination of alkali treatment followed by a bleaching process and then an acidic hydrolysis as well, right? So there are a lot of options for us to source cellulose from. Okay, then once we have a cellulose fiber, what do we do with it? We saw that traditionally the wet pulp molding is a process that is already commercially viable. There are many products out there in e-com websites and distribution channels. You will see food containers, takeaway containers, plates, cups, trays are all molded based on wet molding process. We also noted that in the wet pulp condition, we need a lot of water, okay, because it's based on an aqueous process. And secondly, we have to evaporate this water in a drying operation. So this leads to a lot of energy consumption. Okay. Apart from these two limitations, it's a scalable process. It can be done in large scale, and it has a huge market already in this for this. Then subsequently, we discussed what about having a process with no water associated, right? So we talked about something called dry pulp molding. This involves having a loose pack of cellulose fiber and then applying pressure, temperature, so as to consolidate this loose packing into more stronger, durable container. Okay, so this requires a molding process. We saw those two. There are few. I think we also saw few startups in Europe developing a lot of technologies for this dry-based molding, and it is yet to come up in India or in this large-scale production. Okay, so that is one area where innovation can happen. Okay, the reason why I bring a lot of information about new technology and startup is to inspire you to think in those directions. Okay, cellulose has been there, people have worked with cellulose, but new technologies are needed to meet the current demand for the transition towards sustainable materials. So wet pulp method, molding method is one upcoming method. A lot of innovation is possible. Okay, so if you're creative, you can come up with your own process for this, right? Now I want to build on from there. So wet pulp molding, dry pulp molding, and then we look at few other upcoming technologies. These are all in the startup stage or a pilot stage. I have not seen the big industrial scale production, but I think the route is made for these technologies, right? Now in that line, there is one technique called deep drawing. Okay, if you are a metallurgy student, you will know what this deep drawing is. It is predominantly done in metallurgy. Okay, especially if you have a steel plate, you want to convert this steel plate into some shape. Okay, and we do what is called deep drawing. So what you see on the right hand side is a machine that does this deep drawing. So you can see that there is this two clamp here that will keep a sheet of material in place. It could be paper, it could be metal, and then there is a hot press that will come, that's called the punch. Okay, it will come and then it will push through this gap. Okay, so and then it is held for certain time, certain pressure is applied, and the material will take the shape that the punch is trying to give. Okay, so it is very well known for metals. Now this process has been adapted for molding pulp or cellulose. So the example that you see here, these are all materials that are made through this deep drawing methodology. You can also see there is a cup like material. So we basically use a punch to press paper, cardboard down into a bottomless die. Okay, that means there is no mold in the other side, it just only pushes through a gap. So you can make a lot of materials like trays, plates, and then low depth recipients. You cannot really make all kind of complex shapes. Simple shapes like the spoons, plates, which does not require a lot of curvature, which does not require a lot of depthness. Okay, for example, you cannot make a bottle or a tumbler for that matter. Okay, which requires a deeper uh, depth. And another thing we see is that in the case of paper and cardboard, the produced product would have wrinklings, okay, in this particular process. So that is not very desirable from an aesthetic point of view as well as from a functional point of view. Okay, so these are some of the limitations. Wrinkling is one issue, and paper is not very extendable. Okay, so because of that, there will be tearing, or the depth that you can do will also be limited. Okay, so one option is to mix cellulose with other compounds to add more flexibility or processability. For example, you can actually add starch or PLA, other kind of compounds, and then if you make a sheet of composite material, this can actually take you to little different processing possibilities. You can see this particular paper that talks about the design of this machine and various products that are actually made through this deep drawing method. So what we are saying is this technology is not new. It is there, but used elsewhere, used for mostly for metal sheeting, but that is actually now customized for paper based or cellulose based material. Okay. Now I want to talk about something else. With cellulose, apart from creating containers, cups, spoons, other cutlery, disposable objects, another big area that is coming up is foams, cellulose foams. Okay, so foams, as you know, is very widely used for packaging application, cushioning application, okay, insulation, and sound absorption, and so on. So okay, so there's whole lot of scope for foam based material. These needs are currently met by expanded polystyrene, okay, which we call as a thermocol. Okay, and thermocol is very very nice, very useful, because it is low density. That means the mass per unit volume is very low. Okay, very low density. You can actually mold it in different shape you want. Okay, you can cut it into different shapes. It provides very good thermal as well as sound insulation, right? And then also shock absorbance, especially if you look at your interior of your helmet, right? You want this to be very lightweight because you don't want to carry too much weight. At the same time, it should give impact resistance and shock absorption. So a layer of thermocol is actually there in the inner part of the helmet. Okay, so now we also know that there's a problem with the expanded polystyrene in terms of recyclability, plastic pollution, etc. So there is always a need for replacing expanded polystyrene with another material that could be more biodegradable, recyclable, and eco-friendly. To meet this demand, cellulose foams seem to be the right alternative solution, because like EPS, expanded polystyrene, cellulose foam can also be prepared at very low weight, low density or lightweight. We can fully recycle cellulose, and of course it's also biodegradable. Okay. Now the hope is that wherever we find EPS application, expanded polystyrene application, we should be able to come up with a cellulose based foam that could be used in fields such as biomedical, tissue engineering, cushion packaging, filtering, thermal, sound absorption, insulation, as well as even in construction materials. Okay, so that's a hope. So now let's look at how cellulose foams are made and what are the advantages. So before I go there, can anyone tell me how is it possible to make foam out of cellulose? Do you think it's possible? Any ideas? How can we make cellulose foams? Have you seen foams? Where? Thermocol I already said. Where else? Where have you seen foams? Huh? Huh? Okay. Bed foam. Okay, foam bed. Yes. Where else? Coffee. I mean, have you drunk coffee? You don't see foam on the top, right? Soap, soapy foams, right? If you ever wash clothes, right, you will see foam is. So what is foam then? So now think about, now we know what is foam. Okay, it is seen in beds, cushions, it's seen in soap, it's seen in coffee. So how do we make foams with cellulose? Yeah, air entrapment. Okay, so you say you have to create a air bubble or a gas bubble, and then you have to have a cellulose between those bubbles. Okay, so you're using you can use blowing gas, yes, right? So all we need is maybe I'll just show some figures. Maybe I will get to this one first and then I'll come later. So what you can do is you can take your cellulose dispersion and then you can add some surfactant. Okay, and if you simply stir, because of mixing of air and liquid, air and water, you will see foam formation. Okay, very simple. If you take water, put some surfactant, if you just stir, you will create foam, right? Same process. Now in addition to that, we also have cellulose fibers. Okay, so and then you'll create a very thick foam. Then you can apply a vacuum, okay, remove the excess liquid, then you will be left behind with an interpenetrating network of air filled material, which is called aerogel, xerogel or foam. Okay, so now this is the concept. So foams can be made with surfactant, but now in addition to surfactant, we are also using cellulose. The cellulose are likely to be between these air bubbles, forming the walls. Okay, and that, you know, once you dry, you basically get a solid material that is very soft and sponge like. Okay, so you can see that on the left hand side, there's a foam created with the use of surfactant. So here, this one on the right hand side you see is without surfactant. Okay, if you simply put only your cellulose aqueous solution and if you stir, you can create foam, because cellulose itself will form some temporarily stable foams, and then if you drain, you will get a foam sheet, but that would be much more thicker. Okay, because the air bubbles will immediately start coalescing and it's not going to be stable, so it will have more thicker or more denser material. So that's what this is. Whereas when you use SDS, which is a surfactant, it stabilizes the air bubble when it drains or when it dries. Okay, so that creates enough porosity for the material, so you can get very low density foam. Okay, and this white color obviously is because of cellulose. So that's the idea of how to make foam. So now what options we have? Well, the idea is that we can actually look at any agricultural source for cellulose. It can be based on wood or bagasse or any other rice husk and etc. Any agriculture product can be used for extracting cellulose. And so you can see this is a cellulose, the white powder that you see there, right? Now along with this, you need a surfactant. So commonly used surfactant could be SDS, but then if you want to be a little bit more eco-friendly, you can use starch, polyvinyl alcohol or cationic polymers, okay, as a surfactant, which is basically a foaming agent. You want to basically create a lot of foam, a lot of air bubbles. Okay, and once, so you can see this this picture here kind of illustrates how the foam is going to look like once you stir a solution containing cellulose, surfactant, water in the presence of air. Okay, when you stir, you will see this kind of very foamy substance, and then you can dry under different conditions. Okay, you can dry under vacuum, you can air dry, or you can freeze dry, right? You basically freeze the entire thing, it becomes ice, whatever the remaining water will be ice, then you sublime the ice, so you get a porous structure. Okay, now since it's in a liquid form, you can put in any mold you want. Okay, and then you can dry it, you get a foam. Okay, and by controlling the porosity, how do you control porosity? You control by looking at surfactant concentration, the mixing conditions, temperature, cellulose concentration. All of these parameters will affect your foam property. Okay, so that some optimization needs to be done, and then once you get it, you dry it. The good thing is, whichever foam you create here, these are all biodegradable. Okay, it basically goes back to nature, unlike the expanded polystyrene. Okay, there is a huge scope for alternative foams to EPS, and cellulose foam is the right candidate because we don't have the dearth of raw material. Cellulose you can extract from so many type of varieties. If you get a good source of surfactant, eco-friendly, bio-friendly, abundantly available surfactant, then it's all about this mixing and drying. This I already described. So here there is a company, Stora Enso. As you can see, this is a bottle that they want to pack, and you see there is a cushion, the white cushion that you see here, that is actually a cellulose foam. Okay, you can see it does not look anything different from a EPS, right? It just looks like a expanded polystyrene. It can be molded in a given shape, given form, and thick, right? So here you can see that another foam packaging is designed to keep this particular object, a glass object that kind of nicely goes in and sits. So the point is, just like the way that we can shape EPS in different form, you can also do the same thing with this cellulose foam. So this is a startup. I think it is based in Finland. Okay, Finland, Sweden, you see a lot of startups coming up on sustainable material. So there is a Finland based company that creates this kind of foam. Okay, so what were we saying? Cellulose into products: wet pulp molding, dry pulp molding, deep drawing, and then foam, cellulose foam. The next in line is something called injection molding. Generally, injection molding is used for thermoplastics, right? For example, polyethylene, polypropylene, PET. If you want to convert this resin into a product, what you do is you do something called injection molding. So injection molding is nothing but there is a extruder and then there is a die. Okay, so you basically put your raw material from far end of this extruder, and then the screw will try to transport this resins in this particular direction, and then you also have a heating chamber along the length of this extruder. So as the material passes through, it gets melted, right? It gets melted, it flows like a liquid, okay, at high temperature. Then the liquid polymer melt is injected into a mold, okay, and then this mold will keep this product for a while, and then it cools at this point. Okay, so when it cools, it becomes a solid material. Then you can remove the mold and you take the product out. Okay, so most of the plastic, thermoplastic material that we use are actually injection molded like this, right? So what has been possible with the cellulose is that you cannot use a pure cellulose into this process. Okay, it doesn't work that way, but there are a lot of work has been done where they mix cellulose with other material. In other words, cellulose is used as an additive in other matrix polymers. Okay, so here is one example. You can see it's a very intricate design is printed or maybe injection molded, but this material consists of about 60 to 80% cellulose fiber. It has starch, PVA and water, right? So there are many work where cellulose is mixed with other polymer, just like this case, and then you optimize the temperature and then mold into this. So, injection molding of cellulose is also emerging application. Okay, injection molding machines are already available. As long as you can come up with a biodegradable composition that is injection molded, then you can actually go beyond the shapes that other methods give you. For example, the wet molding, dry molding, deep drawing, they all have some limitation of what shapes you can print, right? They have to be low depth, it has to have open ends, okay? But injection molding on the other hand can create very complicated products, okay? So then if you can think about making your composition, cellulose composition amenable for injection molding, this is also one possibility, right? Now another technology is 3D printing. 3D printing, I think many of you have seen. It is again a process in which you basically take your material and then print as per a design. Okay, just like how we print 2D printing, 3D printing is basically printing in 3 dimensions. It basically uses a printer, 3D printer. So with regard to cellulose, there are 3 kinds. There are something called hot melt extrusion. In this hot melt extrusion, typically cellulose is introduced at very low concentrations, mostly as a filler or as an additive, right? The second type is called gel extrusion, in which case you create cellulose-based gel. Okay, when you make a cellulose at high concentrations with some plasticizer and binder, you can create a hydrogel, and that hydrogel can also be printed using a 3D printer. And the third one is called cold extrusion. In this case, you create a paste rather than a gel. You create a paste with a very high cellulose concentrations, and then you can also print. So some of the things that you see here, these are all 3D printed cellulosic materials. Okay, so again, this 3D printing is still in a more like a prototyping stage. Printing in large scale is a little challenge, because each printing will take, depending upon the design, it can take up to an hour or even more than an hour. Okay, so and generally, if you remember, in the case of wet pulp molding, dry pulp molding, the cycle times were like few seconds, tens of seconds. Okay, so in tens of seconds the product is made, and then you can make new one. So in terms of productivity, those are very scalable, but these ones can give you very high intricate designs, but then in terms of productivity we have some challenges. Okay, so we need to think about coming with large scale production of 3D printing. Okay, but this is also another upcoming area for cellulose. So here we try to kind of compare various processes. So you can see that we have wet molding, dry molding. I didn't talk about powder compression. This is nothing but taking a solid powder and then compressing it and giving it to a molding. Okay, so in a way it is very similar to dry molded fibers. Then injection molding we saw, deep drawing also we saw, and 3D printing and cellulose form. So these are all various options available for cellulose materials. So each of these processes is actually compared with several qualifiers. For example, whether these processes are industrially available, that means whether it is scalable. Productivity, that means how fast you can produce your materials. Environmental damage, that means how much water, energy, other pollution that creates. Novelty, how new this idea is. And then how complex structure we can create. Okay, that also is important. And then how much is cellulose content? Is it pure cellulose or is it added with something else? Now, if you consider this wet molding, okay, the wet pulp molding, as we said, it's already industrially available. A lot of paper mills are already producing this. So it's 5 out of 5. That means it's highly desirable, highly possible. In terms of productivity, because in each of this wet molding there is a cycle time. Okay, so there is some sort of issue there. Environmental damage a little bit because of the use of water and energy. It's now in terms of novelty, it scores less because it's a very, very old technology. You know, it's done in cottage industries also, right? So novelty wise, it's not very big. 3D shape complexity is an average. I mean, it's not too bad like your deep drawing, and it's not too sophisticated like injection molding. It's somewhere in between, so average. Cellulose content is actually, you can use 100% cellulose, pure cellulose. Okay, so the entire product that you create out of that is actually a pure cellulose. So cellulose content is very high. So the wet pulp molding basically wins in the cellulose content and the industrial availability. Okay, but scores very poorly in the novelty. So not a big startup idea. If you go to dry molding, only I think there are few companies that are making machines to do this. So it is not widely available yet. So because of that, it scores less in industrial availability. But in terms of productivity and environmental damage, they are much desired because it does not require additional water, drying, energy requirement is less, productivity can be high. Novelty, the novelty is set as average because it is not a really a novel idea. It is just basically combination of existing ideas synthesizing into a new process. Okay, so that's why its averages. In terms of 3D shape complexity, it is not that great because it again depends on some sort of an open-endedness and shallow depth that is only possible. Again, just like wet bulb molding, dry bulb also has high cellulose content. The product that you get out of the dry molding is purely cellulose. Okay, so I will probably skip the powder compression because it's very similar to the dry molding. When you come to injection, this industrial availability, what they mean, it's very less. Basically means whatever the machine that are there is mostly for customized for thermoplastic resins. So customizing that for cellulose based or cellulose composite is little challenging. Okay, so you have to redesign the entire screw, temperature zones, etc. Productivity, environmental damage, average, novelty is average. But if you look at this 3D shape complexity, it is the most desirable because any intricate shape you want, as long as you have the mold, then you should be able to print. Okay, so it's good. Cellulose content, as I said, there is no product that is completely made 100% cellulose via injection molding. Usually it is mixed with some other thermoplastic resins or other additives, so the content is only less. Then we have deep drawing. In the case of deep drawing, there are existing machines made for metal sheeting can be used. Productivity can be quite high because it's very fast process. You just one punch you get it. There's no holding time. There is no putting pressure and keeping it for certain time. Okay, it's very quick process. Environmental damage average because of energy use, etc. Novelty not great. 3D shape complexity not great because, as I said, it can only make some simple shapes, low depth shapes. Cellulose content can be again average because generally cellulose is mixed with some other additives like starch and other things. Okay, so that there is enough stretchability and extendability. If you think 3D printing, the only place where it wins is in the novelty because a new technology, and everywhere else it is not so great. Industrial availability, large scale, not happening. Productivity, I already said it's going to take hours of time for one product. Damage, not so much. Novelty is very high. 3D shape complexity, not bad. It's average. You can still print pretty much a lot of designs. Cellulose content, because as I said, the ink that you need for 3D printing has to be a gel or it should be a composite with other material. So usually cellulose is added as an additive. Okay, not 100% cellulosic material. Finally, foams. As I said, again, foams are also new materials. Novelty wise, they win, but they also lack the same amount of disadvantages like the 3D printing in terms of industrial scale availability, large scale facility. Productivity also going to be problematic. Environmental damage, this probably because you're going to use a lot of surfactants, you're going to use water, how you're going to manage wastewater, how do you treat water and all that. And 3D shape complexity, it is not that great but not bad either. And cellulose content again can be, this is because again you are mixing with some other surfactants and polymers. So cellulose content is not 100%. But cellulose foam holds a great future for replacing EPS or polyurethane foams for that matter. But only challenge I see is that if you look at foam packaging, especially from polyurethane based methods, well, let me just say this way. So there are two ways in which you pack with foams. For example, if you want to pack your refrigerator, so refrigerator design is known, okay, you know which are the area you want to protect. So typically the corners and edges, you basically cut your foam in that particular shape so that it goes nicely into your carton box and protects the product during the shipping and transportation. So it can be made elsewhere and molded in a particular way that you want. Okay, this is one application. Then there is another situation where the product that you are actually packing is not always a standard size and standard shape. Okay, one of the thing I saw recently was I visited an industry that makes valves. Okay, big valves for transporting gas, oil, water, and etc. These valves come in different designs and different sizes. So there's no one single design for all the pumps, all the valves. So for each time you change your valve, you cannot have different packing material all the time. So here what they do, they create foam in situ as in when you need. Okay, so here they had two barrels. They say chemical A and chemical B. It's basically a polyurethane making system. So they draw two fluids together and then they heat it to induce reaction, and then the outcome of this tube is actually put into a box. It basically pours like a foamy liquid, and then immediately it forms foam and it expands. Okay, so they put the material that they want to pack here, and then the whole foam builds around this shape automatically. Okay, so the foams are created in situ in the shape that you want. Okay, so these are the two currently existing foam application for packaging. So now if you think about cellulose to replace, for the first application, if I already know the design, you can create cellulose foam, mold it in those shapes. Okay, and I think that is doable. But to replace this in situ foam formation through polyurethane, how you would design cellulose foam for in situ application, that is a little challenge, because here you can see the number of steps that we are involved in. So you have to first create a cellulose suspension, then you have to add surfactant, then you have to mix, stir to create foam, then the foam has to be dried. So now if this entire process can be done in industry and then can be molded in particular shape, that is good, that's not a problem. But in the case of a polyurethane based application, where the demand is to create foam in situ where the product is packed. So the challenge seems to be, how are you going to integrate all this process and do everything in the place of its use. Okay, that seems to be quite challenging, and that's where probably an innovation can come. Okay, how do you think about a cellulose foam on demand preparation in a given location, given that all this process has to be integrated together, forming of cellulose fiber, suspension, adding surfactant and stirring, and then drying, and then pouring that foam into the desired shape. Okay, so that is still a little bit challenging. Okay, but the point is that there is a lot of scope for innovation and startup ideas. So that's the whole point. Now, so far whatever I have talked about is about making a product out of cellulose. Okay, so what are we saying? Where do we get cellulose from, and then what do we do with the cellulose? Where do we get from cellulose? We get from agriculture waste, wood, pulp, rice, wheat, straw, etc. etc. Okay, a lot of agriculture products are possible to extract cellulose from. So once you have the cellulose, then we have several processes. Okay, wet molding, dry molding, injection molding, deep drawing, and 3D printing, right, and foams, etc. Okay, a lot of processes we have seen. Now, when you make a product out of any of these processes, their assets are not functionally relevant. Okay, because it may absorb water, it may not have adequate strength. So you need to think about imparting some sort of a functionality. Okay, so this slide is all about what is typically added to a cellulose products. One of the big issue is cellulose will absorb moisture, it will absorb water. So you need to create a situation where it doesn't uh, absorb water, at least for a short time. Okay. So typically various chemicals are added during the molding process itself in the fiber. Okay, when you make this fiber in wet molding or dry molding, in the fiber stage itself, some chemicals are added. For example, this perfluoroalkyl substances or alkyl ketene dimer or alkyl succinic anhydride. So these are all chemicals that are traditionally used in paper industry to be able to make the paper less water absorbing. Okay, at least for a short time. Now the same classical chemicals are also being used in the pulp based products. So as of now, I think the PFAS is now banned in several countries because of its polluting nature. So there is always an opportunity to look for new kind of chemicals that will add hydrophobicity. Okay, so in one of the products that we made in our lab, what we did was to improve hydrophobicity. We would make a polymer which is hydrophilic, and then we would treat it with some sort of a fatty acid, and then the fatty acid will give a coating that will provide enough hydrophobicity. Okay, so we can think about various other ideas also. Another standard approach is to laminate with the barrier film. For example, polyethylene terephthalate or polypropylene films are coated on the outer surface so that you provide enough hydrophobicity, barrier properties, etc. If you don't like the conventional plastics, there are options to do with the bioplastics also, PLA, PHA, these are also possible. So generally these films are made elsewhere and they are pressed against the product so that it basically gets laminated on the surface, providing enough water resistance property and barrier properties. Another possibility is something called liquid coating. Whatever functional coating you want to add, you can do it through a dip coating or a spin coating. Dip coating means whatever liquid that you want to coat your product, you dip your product into that liquid, keep it for some time, and then take it, drain out, and then dry it. Okay, so that would give you a nice coating of the surface. The second thing is called spin coating. You take your product and you put a drop of your liquid and then you spin the product, okay, and then it gets nicely spread into a thin film. Okay, so these are very conventional techniques of coating the surface with some functional groups. Then there are new technologies called molecular deposition, where you add chemicals or species at atomistic level, so you can't really see on the surface, you can't touch and see. Okay, it is done at a molecular scale. An example is chromatogeny coating, in which so there is a startup, Web CTP. What they do is they add a fatty acid or a wax into the fiber and treat it so that the cellulose fiber get coated with the fatty acid and imparting inherent hydrophobicity. There is another startup, Silcoa. This is a French based company. They are coming with something called atomic layer deposition to create a ceramic coating on the material to provide hydrophobicity. Okay, so I can see that not only the new technologies of cellulose products, but even the functional coating, barrier coating, there is a lot of innovation, a lot of startups are coming up there. So if I have to say finally about cellulose, so cellulose is the first natural polymer that we have been discussing. It's naturally available, abundantly available, renewable, biodegradable. So we should try to make best use of cellulose. The good thing about cellulose is it's not edible product. So we are not really competing for food security issues. Unlike starch, for example. Starch is food. So if you make too much material with the starch, then it can actually compete with food security. But cellulose, on the other hand, is not consumed by humans, at least. So it is not a food product. So we can use as much as we want. That also means that we have to create technologies, innovations, as you can see, in the way that we can extract economically, sustainably, okay, of cellulose from raw material. That's one place where there can be a lot of innovation. How can I eliminate using harsh chemicals? How can I eliminate alkalis and acids and bleaching agents? Can I use milder chemicals to extract cellulose from agricultural waste? So a lot of innovation is possible there. The second possibility is coming up with new kinds of technologies, new kinds of processing technologies to convert cellulose into a product, into a given shape, bottles, trays, foams, all kinds of things. Okay, so that is an open space. Okay, there could be a lot of possible innovations there. The third thing is what kind of coatings that we add to this product to enable hydrophobicity, water resistance, and strength, etc. Okay, so if you want to impart all this functionality, how do we coat these material with new chemicals, but again eco-friendly chemicals, renewable chemicals, etc. So therefore, it is safe to say that cellulose is the ideal candidate for circularity in materials, for some sense, from the packaging point of view, from the single use point of view, from the food container point of view. So cellulose seems to be the best solution for circular economy because it's largely available in nature. Production industry is also in place in few technologies, biodegradable, and the recyclability is also very mature for cellulose. Okay, because paper industries have already shown how to recycle paper. So we should be able to use the same technology for recycling cellulose-based material. So it looks like it's a very nicely placed for cellulose economy. Okay, great. That's all I have, and we have 5 more minutes. I just want you to kind of go through this website and just check out yourself what these people are making. Right. So there is one more here. I think I showed. Yeah, this also. Stora Enso for foams. Maybe I should put all of them together.